Potential energy of an electric dipole in an electric field. Let us consider an electric dipole is placed in a uniform electric field E, making an angle theta with the direction of the electric field E. In order to explain this, what I'm going to do, I'm going to consider this information and draw a figure. So here is my figure or my picture where you can see these lines are the direction of the electric field, and since this is an uniform electric field, that's why the lines are parallel to each other. Now we have an electric dipole where this is the negative charge Q and this is the positive charge Q, and they are separated by 2l distance apart, and they are making an angle, and I should say the electric dipole is making an angle of theta with the electric field, and if that is the case, then we have a force F is equal to QE working in this direction at charge plus Q, and a force of negative QE is working in this direction on charge particle negative Q. Then we will write the torque produced on the dipole is given as tau is equal to P times E, which is basically the vector product of electric dipole moment P times electric field, and we know that the vector product of two vectors is basically with a sine theta, so we'll write tau is equal to PE sine theta, where theta is the angle between the electric dipole and the electric field. Now we need to find the work done. Let the dipole is rotated from an angle theta 1 to theta 2, then the work done by the dipole is given as W is equal to integration from theta 1 to theta 2 tau d theta, where tau is basically P sine theta. So let's substitute this value, and if we do that, we will write W is equal to integration from theta 1 to theta 2 P sine theta d theta. Now let's simplify further, and if we do that, we will take P outside because P is a constant, and we will write W is equal to P integration from theta 1 to theta 2 sine d theta. Now let's integrate sine d theta, and if we do that, we will write W is equal to P, and the integration of sine theta d theta is negative cosine theta, and my lower limit is theta 1 and the upper limit is theta 2 from here and here. Now let's simplify further, and if we do that, we will take this negative outside, and we will write W is equal to negative PE inside the bracket cosine theta, lower limit theta 1 to upper limit theta 2. Now let's substitute the lower limit and the upper limit, and if we do that, we will write W is equal to negative P cosine theta 2 minus cosine theta 1. Let's simplify further, and we will multiply this negative inside, and we will get W is equal to PE cosine theta 1 minus cosine theta 2, because this negative times cosine theta 2 is negative cosine theta 2, which is over here, and negative times negative cosine theta 1 is positive cosine theta 1, which is over here. So our work done is W is equal to P cosine theta 1 minus cosine theta 2. As we know that the work done is stored as the potential energy of the system, so basically we can write W is equal to U, and we will replace this W by U, and we will write U is equal to PE inside the bracket cosine theta 1 minus cosine theta 2. So as we can see, we have W is equal to PE cosine theta 1 minus cosine theta 2. Now let's consider a situation where theta 1 is equal to 90 degree and theta 2 is equal to theta. And if we substitute these values in this equation, then we will get U theta is equal to PE cosine 90 minus cosine theta, because theta 1 is 90 and theta 2 is theta. And we know that cosine 90 is 0, so we will write U theta is equal to PE inside the bracket 0, because cosine 90 is 0 minus cosine theta. And if we simplify further, we will write U theta is equal to negative PE cosine theta. And let's write in terms of the dot product of two vectors, and if we do that, we will write U theta is equal to negative vector P dot vector E, where P is the dipole moment or electric dipole moment and E is the electric field. And this is how we will define the potential energy of a dipole in an electric field.